but now we're going to show a few more things. So another VSA we did is the 11 one. This is the one that uses the extra fields. So you can see that this particular file, which is also configure sample, right here, its file name is B, which should be 11 long, but we only declared it as 7. So first 7 letters of this word are file name, and the rest, as defined here, is just extra data. And by processing the header, Zip really needs to know where the next file in the archive is, and that's the size of that local header, plus the size of the name string, plus the size of the extra data, plus the size of the file comments. Now, since some software didn't process that correctly, they wouldn't be able to find the next file in line or the end of the archive. It's the same thing with the second version of the same vulnerability, but here we didn't hide the malicious sample. We have hidden the file before that. So by adding this extra 256 zeros, we were able to break some archive processors because we thought that some of them would generically search for the next entry in the central directory. So we added some space just to test out what's their tolerance for this kind of stuff. And as it turns out, it's 256 bytes. Now, talking about zip file format, this is that particular file, SFX file we talked about. So if I was to open this file with, let's say, WinRAR, the thing I would find is this image, which was appended to the SFX file. And that's my good friend Donkey. Now, if I would to start this SFX file, the data that would be extracted to, let's say, new folder, wouldn't be a picture of my good friend, but it would be the malicious payload we compressed. So let's say new folder, so you see something happened. Okay. So inside the new folder, you have malware.bin, which is compressed configure sample. So the SFX executable itself knows the correct content to decompress, but because we are searching for this particular content from the end of an archive, we weren't able to find that packed content. We found the picture of my good friend. Now, we could really go into detail of inventing our own file formats here, but we're not gonna because we're kind of low on time. What we're gonna show is the modification of the SFX module. So inside the module, of course, there's an archive which needs to be decompressed, and we changed pretty much everything to the layout of the archive. Now, for the SFX module to be able to decompress that kind of content, it needs to be aware of the file format type. So the binary itself, the SFX module, was changed to recognize this new format we invented. And if you try to open this SFX executable with any software, it's going to tell you that it has no idea what it is, of course. But if we start it, we are able to decompress the protected content, and this is why no software that works with archives will be able to successfully decompress it. And here again is the configure sample. But we were surprised to find that some antivirus vendors were able to scan this particular archive. And the way that they did this is they looked for the compressed data itself. So we didn't change the compression algorithm or anything like that, we just changed how the headers look. And some antivirus vendors were able to detect that and decompress data correctly. So when talking about RAR file format, this is what we talked about. By declaring this first block as a temporary one, we can protect this archive from modification. So if I was to start this archive, it shows a configure sample. By just by adding a new file to it, we will successfully break it. And it's broken. So you can protect your archives from being modified like this if you really want to. But this process can be reversed. I'm going to show you how to do that right now. So we just do a little bit of hex editing. No big deal. So we switched off that temporary flag. See the new size, which is now D. It's not 11. So D, and we really need to correct the header checksum for this particular bit. So we compute the hash, see that it's CF90, which was the default value. And if we save that, we will be able to see both the malicious payload and the one we have compressed, and the archive, of course, works. So this is reversible. Okay, that's the first demonstration. We have another one, but we got to get there. So to get there, we have to talk about the Nix engine, and that's the tool we are presenting today. What's important about the Nix engine is who is Nix and why have we chosen her. So Nix is the Greek goddess of night, and we thought it would be kind of fun if we have a Greek goddess of night watching over our files. So what does it do? It does the archive pre-processing, so this isn't an extracting tool, though it does have an ability to recover data. So recovery is done by extracting the data without really extracting. So the data you recover is still in same format as the archive is. So if you recover damaged files from the zip, they're still zipped. You have to decompress them later, but their headers have been fixed, and you can use that kind of files. Now, it acts like an exploit shield. In the process of building this particular engine, we wanted to have an engine that's able to process the entire archive and look for these anomalies and skip over them and make us feel safe, because there were some exploits in the wild that acted like executing remote code in your machine if you were to process this kind of archive. So we wanted to be safe from this. We also wanted to be able to generically detect all hidden data inside it. Now, how can you use it? It's a free library. It comes with its SDK. It's going to be available on our website soon. It has a Nix console, which is an example of how to use an SDK. And it's we converted it to a plugin for Total Commander and Power Archiver. So if they cannot process the archive, our plugin is going to step in and enable you to view the content and recover the data. Now, the functional groups are, of course, we support identification of these 4 file formats. It's ziprar, cat, and gzip. We enable content browsings, which means you can traverse the archive one file at a time. So just by calling get next file, for example, you would be able to go through each and every file we found in the archive. You also get all the information possible about the pack content, so the compressed size, file time, file date, attributes, is it password protected, is the name Unicode, everything about the archive. Does it split in multiple volumes? Everything about the archive that is present in the headers and valid, we give back to the user. We also do archive validation. So what we wanted to know is if the archive was corrupted, and if it was corrupted beyond recovering. So this is a pretty simple process in which we determine if the damage is beyond any kind of useful data recovery. And the output you get is either, yes, the archive is valid, no, it's not valid, but yes, you can fix it, or the archive is so broken that there's no use of doing anything with this file. Now, we also did, of course, search for steganography content, and we did this generically. So the idea behind it is to generically support any kind of Stego implementation done to the archive. And we do this by basically mapping out the file and seeing which parts of the archive are attributed to the pack content. If there's anything between the pack